Want to make a quick comment here. We will be deriving new mathematics from the old, meaning we are going to derive theorems from the definitions and so on and so forth, and from the some existing theorems to derive new theorems or new corollary and so on and so forth. Now, at this time, we have established theorems like previous examples. We established two very simple theorems using only the basic algebra normally taught in secondary school, and also the fact that integers are closed under addition, subtraction, and multiplication. What does that really mean? Let me give you a little quick explanation here. When we say integers are closed under addition, that means this. If you pick any integers, when you add, it will be the result is integer. So that's why we call it closed. So the result is back into integer. Similarly, if you pick any two integers, when you subtract those two integers, the result is back to integer. So that's so-called closed under subtraction. And for multiplication integer, if you pick any two integers, the product is certainly an integer. That means integer is closed under multiplication. Here we don't have the division because division will not be closed. For instance, you pick two integers, say 1 and 2. So 1 divided by 2, which is 0.5, is no longer integer. So therefore we say division is not closed. Okay, integer is not closed under division. So only the addition, subtraction, and multiplication. We also use the definitions of the term in the theorem themselves. So all those are the things that we used. We used nothing more than that. So in the future, when we ask you to prove something directly from the definitions, you just use those very basic stuff. You do not assume more than that. So you should restrict yourself to this approach. Okay. A term, a corollary, is a statement whose truth can be immediately deduced from a theorem that has already been proved. So usually we call a theorem as a pretty important and fundamental and big result that derived from definitions and basic properties like basic, just what we mentioned here. And if from the theorem, which is pretty general statement, if you can derive another smaller theorem, then we call that pretty quickly, then we call that statement as a corollary. Okay, so sometimes the difference is subtle, but well, I think the more you see, the more you understand what a corollary is. Now we are going to assume the 7 properties listed below. So this, I would say, these are sometimes, some of those are good examples of corollary because they can be derived quickly from some other theorems. So well, again, we just assume these 7 properties have been proved. And actually, we have not proved them, but we are going to assume we cannot prove all the things. We have to assume some basic things so that we can move forward to prove more, more complicated statements. So these are the fundamental things that we are going to assume. I would say these are good exercises for you to practice your proof skills. These are really easy to prove, but it certainly involves how to translate the term correctly, how to translate the statement using quantifier correctly. What do you assume? What do you want to prove? What does it take for you to make the conclusion? All those skills needed for the proof, you can exercise them here. So now the first one is the sum products difference of any two even integers are even. So that means adding, multiplying, subtracting two even integers, the result is going to be even. The sum and difference of any two odd integers are even, so when you add or subtract two odd integers, they are even. The product of any two odd integer is odd. The product of an even and odd integer is even. The sum of any odd and any even integer is odd. Difference of odd and even is odd. Difference of even and odd is odd. So those are the very intuitive one, but they're good exercise for you to prove. Now let's prove another more, a little more, a step up, I would say. So let's prove this. If a is any integer and b is, A is any even integer and b is any odd integer, then a squared plus b squared plus 1 whole thing divided by 2 is an integer. That's what we want to prove. Okay, now let's prove. So this is if a is even, so I'm going to say for all a, b, and a, b from integer, if a is even and b is odd, then a squared plus b squared plus 1 over 2 is an integer. That means we're going to say then this is an integer, right? Okay, this is what we want to prove. Okay, now to prove, I'm going to say let a be even, b be odd. Want to show a squared plus b squared plus 1 divided by 2 is integer. That's how you interpret this statement. This time, to show something as integer, this time is sometimes you may not be able to figure out, okay, what does it take for me to show this as an integer. Some of you may think, okay, in order for this to be integer, seems like I can show, if I can show this guy is even, then even divided by 2, it should be divided evenly. So therefore, I know the result is actually gonna be integer. So that's sometimes, if you have a little more thoughts about it, that's probably give you a little bit of hint on what you want to get to, right? Now let's begin with so now because let's take a look at the detail of this guy. It involves a square. So now because a is even, now therefore let's take a look at this. So it says the product the sum products difference of any two even integers are even, right? So because now therefore a square, which is a times a, which is the product of two even integers, because a is even, so this is a product of two even integers, is even by the property number 1 listed above, right? Okay, so you see that I'm deriving a new result based on some properties here. And now it also involves b squared. So let's take a because b is odd, okay, and let's take a look at, it says the product of any two odd integers is odd. So therefore we know, therefore b squared, which is b times b, is odd by property number 3, okay? Property number 3 listed above, okay? Now, therefore, so I'll have to continue from here. Therefore, a squared plus b squared, which is a, a squared is even, b squared is odd. So actually, let's try to find the sum of an odd and even is odd, right? So therefore we can conclude that a squared plus b squared is odd by number 5 listed above. The sum of an odd and even is odd. And therefore, we just derive one by one, a squared plus b squared plus 1. Now, we already know that this is odd, and this is 1 is odd, right? So it says the sum of any two odd integers are even, so therefore the sum of two odd, so therefore we know these two, the sum of these two odd integers will be even, is even, because a squared plus b squared is odd and 1 is odd, and by property number which one? Which one do we say? Any odd the I'm sorry, just number 2, so I lost track of myself. So and by number 2, right? So therefore we can make this this conclusion. So now that's what we just talked about, right? So if you know this is even, then it should be divided by 2 evenly. So now, but if you remember, therefore we can say a squared plus b squared plus 1 is equal to 2k for some k. For some k, that's how we, for some integer k. That's the definition of even that was introduced in an earlier section. So now, therefore, if you divide both sides by 2 using the basic algebra, we can see that k is equal to a squared plus b squared plus 1 over 2. And k, we already know that k is an integer, right? So is an integer. So now we finished that. We finished that because that's what we want to prove. That's what we want to prove. So therefore, we now just write in one more step. This guy is an integer, and then we are done. Okay. The only thing that I think I need to revise. I probably want to say because here therefore I have this guy, and because k can be written as a squared plus b squared over 1 over 2, so I would say because of that, and also k is an integer, so I actually want to break this into 2. K is an integer. Therefore this guy is an integer. So you can see that sometimes even when I write my proof, sometimes I have to make a little adjustment so that the flow of the argument is the best. All right, let's close this section by doing the very last one. This we call it a corollary because it doesn't take too much to prove this result and directly from other results, okay, by another theorem. So prove that the double of a rational number is rational. So in other words, I'm going to rewrite this. If R is rational, so double a rational number, that's why. If you say for R in real, that's completely okay, but you can certainly skip that. That doesn't affect too much. So if R is rational, then the double of this guy, so then 2R is also rational. Okay, here's my proof. Suppose R is rational. Want to show 2R is rational. Okay. Now, this time, the reason we call it corollary, because oftentimes this comes from a theorem, Let's review one of the theorem we already proved. We say here this theorem, it says we already proved that the sum of two rational numbers is rational. So the sum of two rational numbers is rational. So I'm going to try to derive the result that we are trying to prove using this particular theorem we already established. Okay, so in other words, my goal is we can certainly derive this using the definition, but this is corollary. I want to show you how to derive quick results from a theorem that's already established. That's why we call this as corollary. So now, by using a previously established result. So now, because R is a rational, and therefore R plus R should be irrational, should be also rational. Why? This is by theorem 4.2.2, right? We just mentioned sum of two rational is sum of the two rationals is rational. So here sum of two rational is rational. Now because R plus R is 2R, right? And now therefore this guy is rational. Okay, therefore 2R is rational. So do you see that we quickly prove this by using a previous result? Oftentimes, here I break that into two steps. I would say this is sufficient. You can combine these two into one. I would feel, hey, you really don't need to make another line. You can just say, now R plus R, which is 2R, therefore it is rational by the theorem 4.2.2. All right, this concludes this section.